Ideas can be amusing, invigorating, or just basically functional. A very special idea, however, can be so compelling, it can change the world. One of those very special ideas that is particularly identified with us and with our world today is also one of man's oldest dreams. Flight. A tough egg that refused to hatch for centuries. Once out of the nest, wow. Of all the wonderful airplanes which have evolved from the idea of flight, perhaps none has touched our lives so directly as the passenger transport. It beats the mythical 7-league boots not by miles, but by continents. Every day, thousands of passengers, from babies to grandmothers, nonchalantly cruise high above the earth at velocities approaching the speed of sound. Now, why are we so inclined to entrust ourselves and our loved ones to these mechanical flying machines? Because they have earned our trust. Because mile for passenger mile, they are the most reliable transportation that there is. And because they allow us to make the most of our most perishable commodity, time. Yes, the airline business is an idea that is here to stay. Each of these jetliners is a triumph of scientific ideas. And in many ways, each is similar to the others. But it is the differences that are noteworthy. For these differences can drastically affect airline profitability. The most different of today's jetliners is this one. The L-1011 TriStar, manufactured by Lockheed. To put it directly and without qualification, the TriStar is the most technologically advanced jetliner in the world. It is so significantly different that if you are an airline or a passenger, you should know about it. In order to understand the L-1011, you must know something of the environment in which it was created. You see, the circumstances surrounding the birth of the TriStar demanded that it be the best, or that it not be at all. And this idea of best is what set it apart, made it different. In the 1960s, Lockheed was not involved in the commercial transport business. However, while competitors made jets for airlines, we were busy in other areas. Lockheed developed Polaris, the first missile to be launched from underwater. Lockheed created the SR-71 Blackbirds, the fastest, highest-flying aircraft in the world. Lockheed developed Deep Quest, which probed the oceans at record depths. Lockheed built the C-5A Galaxy, the largest military airlifter in the world. And Lockheed designed and built nearly half of all the satellites orbited by the United States. Technology. During the 1960s, Lockheed burgeoned with technology. We just didn't produce a commercial jet. Now, while this wealth of technology was accruing at Lockheed, significant advances were being made in other fields of research as well, particularly among engine manufacturers. It was the development of this engine, the high bypass turbofan, that ushered in the current era of wide-body jet transports. More powerful, it could propel larger aircraft at lower cost. This was a better idea of revolutionary impact. And as you might expect, Lockheed wanted a share of that market. But we were on the outside looking in. Clearly, airline customers with long-standing successful relationships with other manufacturers would not readily abandon those ties. In order for Lockheed to break back into the airline business, they would have to do what successful entrepreneurs have done since the dawn of commerce. Produce a better product. The L-1011 would be best, or it would not be. We would start from scratch, from a blank page. With no ties to old designs or old methods, we looked ahead with fresh ideas. The spectrum of Lockheed's extraordinary technological expertise now focused on this airplane. We began with an investigation of the basic materials from which the L-1011 would be made. For example, stress corrosion was a chronic problem with wing skins. Lockheed examined a number of alternative aluminum alloys until they found this one, which was inherently resistant to stress corrosion, 7075 T76. The new material was a little heavier than the others, but all in all, it was the best. Corrosion can cause trouble in the fuselage as well as the wings. Many airlines consider corrosion their most expensive maintenance problem. In order to combat fuselage corrosion, Lockheed made a bold decision to utilize advanced metal bonding techniques. One of the many benefits of metal bonding is the retention of the protective coating on both the front and the back of the basic aluminum stock. In the traditional approach to making a part, such as a window panel, the part is fabricated of thick aluminum and the excess material is milled away. Unfortunately, the milling process also removes the corrosion resistance. After layup, the outsized TriStar fuselage panels are permanently bonded in the heat and pressure of a gigantic autoclave. Let me show you a finished example. Using bonding techniques, high stress areas around windows, doors, and cargo hatches are built up using extra layers of aluminum. No milling is required and no protection is lost. Let me show you something else. Bonding eliminates the need for some 200,000 rivets and fasteners on the TriStar. That's 200,000 fewer holes to crack or corrode. There are many other facets to the TriStar's anti-corrosion systems and many other benefits as well. Suffice it to say, the L-1011 TriStar is the most corrosion-resistant airliner in the world. Now, what about the shape of the airplane itself? The aerodynamics? Well, I must admit, it looks very similar to other wide-body jets. But remember, as I said earlier, it's the differences that are noteworthy. Let me show you what I mean. Let's start up front with the windshield. Notice that it's contoured, not flat. This curved shape reduces drag and cockpit noise. Also, the windshield is tough and lightweight. It's made of thick plastic covered with a thin sheet of tempered glass. A bird won't go through. Neither will a 357 Magnum. Ultimately, of course, a windshield is to see through. And since ours is the largest, the TriStar pilot has the best view. And that's something to think about in today's crowded skies. Impressed? Okay, let's take a look at some more reasons why the L-1011 is different. The rear engine is mounted down on the center line of the fuselage. Its air intake is through this large, gently sloping S-duct. In a preliminary design, we had originally considered placing the engine right up in the fin. However, in order to do that, it would have required an additional 800 pounds of special bracing, linkages, things like that. 800 pounds. Aside from the weight savings, putting the engine down on the center line of the fuselage contributed to the TriStar's aerodynamic fineness. But how did this affect the placement of the wing-mounted engines? With the tail engine nestled down below, the rudder could be full-sized to provide maximum directional control in case of a wing engine out condition. Now, you might ask, why do you want to put your engines further out on the wings? Because there are some major benefits to be gained. By placing your engines further out on the wings, they reduce bending moments due to flight air loads, and therefore reduce the structural weight of the wing. The landing gear can be more widely spaced to provide better stability in crosswind landings and for improved weight distribution on the runways. Now look at this. There's room for a larger inboard flap, and that means more stability at low speeds, like when you're landing. And another thing, the farther you keep the engines out on the wing, the higher off the ground they are. And that's important. Unless, of course, you want to use your jet engine as a vacuum cleaner. Now, keeping those engine placement benefits in mind, let me digress for a moment back to those traumatic days in 1973 that shook the world. Petroleum supplies slowed to a trickle. Prices soared. We're still feeling the aftershock, with jet fuel jumping overnight from 12 to 30% of airlines' operating budgets. Fuel efficiency became the engineering byword. But where, with an airplane, does fuel efficiency begin? Well, you can start by improving it aerodynamically. Lockheed had decided in the final design of the L-1011 to incorporate the employment of outboard ailerons during cruise in order to improve handling qualities. Because of this, a stiffer wing was required. And it seems by making them stiffer, they were ideally suited for extending. So we added 4.5 feet each wingtip. Now you might think if TriStar can spread its wings some 9 feet, so can all the others. But not without stiffening their wings. The added weight required for such an extensive beef-up would simply cancel out the benefits in increased lift efficiency. And with the L-1011, those full-time ailerons could be used to relieve the loads caused by the increased span. If you add accelerometers out here at the wingtips and back at the center of gravity and tie them together with a computer, presto, you have aileron control at almost the speed of light. Well, perhaps not quite that fast, but quick enough to dump excess loads and smooth out the ride to boot. That's what we did. We call it active controls. Together, active controls and a longer wing allow the L-1011 to get more than 3% farther on every gallon of fuel. At today's prices, that works out to be about $350,000 saved per plane per year. Ah, you think that's good? Well, let's take it a step farther then. Today, airplanes fly around with a download on the horizontal tail. but this wastes fuel because of the additional drag. If you balanced the airplane to reduce this horizontal tail load, you could save an additional 2% in fuel consumption. That's more than another $200,000 per plane per year. Right now, on the drawing boards at Lockheed, we're developing a system that will balance the aircraft to require less aft load by putting a fuel tank back here in the tail. It works something like this. After takeoff, fuel is pumped from here back to here. Then, before landing, it is pumped back again. For even greater fuel savings, we're looking at a more sophisticated system for a further aft CG loading envelope. This design incorporates an active control system in the current horizontal stabilizer to produce the necessary stability characteristics. We're calling this relaxed stability with active controls. Sounds a little like walking on a tightrope, you say? Not really. Let me show you something that will make this idea perfectly sound in the L-1011 TriStar. This is totally unique in wide-body aircraft, a flying tail. It works a little like a bird's tail and a whole lot like some of our hottest jet fighters. And what does it do? Well, lots of things, but mostly it provides unequaled maneuverability when you need it, like when you encounter wind shear or upset problems. And you can forget about accidents due to mistrim, because with a tail like this, with the entire surface is working to achieve rotation, you're going to take off regardless of how your trim is set. So, what do we have? An airplane with a big, full-sized rudder, large inboard flaps, widely spaced landing gear, fuel-efficient wing, and that incredible flying tail. It's a package of superior control surfaces not found in any other airline. Now, what did we choose to propel all this advanced design through the skies? The Rolls-Royce RB211. This engine features a three-shaft design, which means it's shorter, more rigid, and very durable. It also means it responds quickly to throttle position, since each stage has its own shaft. In fact, the RB211 can reach full power faster than any other wide-body engine. And that's something you really want in case of an engine out or go-round situation. Oh, one more word about durability. Not long ago, at a takeoff just like this, but in Africa, an RB211 ingested one of those big African buzzards. And the score? Well, the engine kept right on humming. On one thing more, the RB211 is not only the most durable big fan jet, but the quietest. Okay, Lockheed designed a wide body which incorporated the safest, most effective control surfaces, the most durable, quickest, and quietest engines, and the best corrosion protection of any commercial plane flying. Now, into this superior package, they would design a system of avionics which in itself would put the TriStar 5 to 10 years ahead of the competition. Which started with a layout of the cockpit. Note how spacious this place is, how uncrowded. Note the uncluttered displays. Up here, the flight control status display panel lets the pilot know at a glance the status of his flight controls. Down here, navigation and fault isolation displays. And of course, that big greenhouse-like windshield. This cockpit couldn't be more logical or functionally designed, even if pilots had designed it, which is, of course, precisely how it was designed. Now, if you think this panel looks more like a space systems panel than a flight engineer's station, you're partly right. Notice the virtual absence of toggle switches. The L-1011 uses space-age switch lights, which were originally developed for the Apollo program. Combined with flow diagrams, the switch lights reveal at a glance the condition of the system they control. Failed, open, or closed. Also note the extensive redundancy on all systems. There are 4 separate and independent hydraulic systems. It would have been far simpler to have had only 3, one driven by each engine. But with an eye to the vital importance of hydraulic power, Lockheed was not satisfied with the easier approach. There are 4 electrical systems, 3 environmental control systems, 2 separate automatic landing systems, each with dual computers, and so forth. In fact, every avionics system on this plane required for an on-time departure or an on-time arrival has at least one backup. But the extensive redundancy of these systems is only one aspect of what makes the avionics of this plane unique. For example, take the fault isolation panel. It monitors the status of over 40 systems. In the 1970s, Lockheed's fault isolation systems were the state of the art. And now with a digital computer, with its vastly increased word capacity, it will remain so in the 1980s. Another system that saves fuel and reduces pilots' workload is called the Flight Management System, or FMS. The FMS monitors airframe conditions and data from several avionics systems in determining optimum economy throughout climb, cruise, and descent. The FMS also does clever things like storing the pilot's flight plan, calculating his fuel cost at his next stop, or advising him how to react to the loss of engine power. The obvious value of FMS will soon cause others to follow Lockheed's lead. But you find it now on the L-1011 TriStar. Another system that exists now on the TriStar is Autoland. For over a decade, Autoland was the only system the FAA would allow to land in 0-0 weather. Now, I want to show you something that not only makes the TriStar's Autoland system superior to all other Autoland systems, but is totally unique to the L-1011. Come along. Lockheed calls this direct lift control, or DLC. What it does through a computer is to dump exactly the correct amount of lift to maximize a smooth, precise glide path throughout the landing descent. With DLC, response time is 10 times faster than with elevator-guided descent. So, fore and aft pitching is practically eliminated throughout the landing approach. Okay, let's go up front and see what an Autoland looks like. Oh, by the way, another thing we passengers fully appreciate is this sense of space. Even when filled, the L-1011 with its high ceilings and double aisles gives this feeling of room to spare. The cabin is warmed by radiant heat. The air changed every 3 minutes. The TriStar customer is kept as comfortable as modern technology allows. Oh, here's something the stewardess will appreciate. This wide cross aisle and the extra room that it gives her to work in. Oh, here we are, about to start our landing. Since we have no visibility problem today, we'll demonstrate our confidence in this system by making this a hands-off landing. In actual operation, the pilots would guard their control columns while carefully monitoring several system status readouts. If the four computers that guide the approach don't agree, the pilot can simply take over and complete the approach or make a go-around. Rollout is also a function of auto-land. The L-1011 would be best, or it would not be. And so it was, and still is today. That's no small achievement, considering the new technology that has evolved over the past 10 years. The key to TriStar's sustained superiority is basic L-1011 program policy. We will continuously develop and test new systems, incorporating them into the production aircraft as it becomes cost-effective to do so. Think of it, an ongoing policy to create and nurture fresh ideas. Let's take a look at some of the new developments. Take a look at this. New integrated flight displays will give the pilot clearer, better, more comprehensive information. A digital computer has been incorporated into the autopilot system. A laser gyro has been flight tested in a TriStar. It is proven to be as accurate as other inertial reference systems, yet its basic cost is half that of existing systems and is expected to reduce maintenance by over 75%. And strong, lightweight composite materials are being developed to replace aluminum parts and reduce the L-1011's weight. A combination of enhanced aerodynamics, such as relaxed stability with active controls, and an improved lighter weight engine will make the L-1011 even more fuel efficient than it already is. There are a number of reasons why an airline will select one airplane over another, and many of these reasons are not directly related to the technology of the aircraft itself. Financing, route structure, equipment compatibility, business relations of long standing. These are just a few of the deciding factors. We feel it's significant that most of the world's largest airlines have selected the L-1011. For them, technology was a decisive factor. What this means for today's customers and for those of the future is they can rest assured that they've invested in the most advanced technology there is. And the passengers will appreciate that as well.